Time to rock. Yeah, that was not my catchphrase, by the way. No. Okay, so today we're going to solve insert into a binary search tree, and yeah, so let's do fast. Let's read the question. The question is: you're given a root node of a binary search tree BST and the value to insert into the tree. Return the root node of the BST after insertion. It's guaranteed that the new value does not exist. Okay, so this is what you're trying to say. You have a tree and you're given a value, insert into it. But this is not just any tree, this is a binary search tree, BST. So I guess we should first start by explaining what a BST is. If you don't know what a BST is, a BST is a special kind of tree that follows a protocol. And the protocol is when you get to a particular node, when you get to not a particular, any node you pick. So if I pick 2, all the values less than 2, all the values to the left of 2 are actually less than 2, and all the values to the right of 2 are greater than 2. So yeah, picking 2, 1 is less than 2. So yeah, it passes. 3 is greater than 2. It passes. Let's say I pick 4, right? 4 is greater than 4. 7 is greater than 4. So it's at the right. 2 is less than 4. It's at the left. 3 is less than 4. It's at the left of 4. So that's basically what a BST is. Now you're inserting into a BST 5. So 5. The reason why we have a BST makes for searching faster, right? Because of it's just like binary search. You know when to go left, when to go right. So when you're inserting, so you know where to insert. You follow the protocol to insert. I want to insert 5. I know that 5, first of all, since I want to insert 5 and I'm starting from node 4, I know that 5 would be at the right because of 5 is greater than 4. When I get to the right, I get 7. Will 5 be at the right or left? Because of 5 is less than 7, 5 will be at the left of 7. So we eventually have 5 at the left of 7 here, and that's what we have here. Mind you, the question says you can solve it any way you want as far as you return a valid BST. So you could eventually solve it this way and get a valid BST. This is also a valid BST. If you take the value 2, all the value at the right of 2 are greater, all the value at the right of 1 are greater. If you take value 7, all the value at the right of 7 are greater. Yeah. So that is that. Okay, I guess I should just let me explain it in case you didn't get that explanation. Let me explain it better using this same BST that we have. Should I use this? Yeah, I think I should use this. 40 20 60 10 30 50 70. Let's see if I can remember that. 40 20 60 60 10 60 10 30 50 70 50 70, and you want to insert the value of 25, if I'm right. Yes. So yeah, explaining BST, let's try to draw the BST of this. If we try to draw the BST of the first value is 40, the next value is 20. We 20 go to the left or right? To the left, because of 20 is less than 40. Then the next value is 60. Will 60 go to the left or right of 40? If you go to the right, because of 60 is greater than 40. 10. Will 10 go to the left or right of 40? 10 will go to the left. Will 10 go to the left or right of 20? It will go to the left. 30. Will 30 go to the left or right of 40? It will go to the left. Will it go to the left or right of 20? It will go to the right. Yeah. So it's not very hard, right? 50. Left or right? Right. Left or right of 60? Left. 70. Left or right? Right. Left or right? Right. Now we want to insert 25. So 25, left or right? Left. 25, left or right of 20? Right. 25, left or right of 30? Left. So our 25 will be here. And that is how you solve it. So yes, we're going to solve it pretty much like this, but we're going to use recursion. We're using recursion because of, why not? We're using recursion because this is a true question, and yeah, recursion is I guess the way. I mean, you could solve it by going, but nah. Recursion is the way. It's a tree. You need to recurse. You need to learn how to recurse. Yeah. So how do we do recursion for this? Let's try. So if you're not familiar with a recursion function is a function that calls itself, and the template of a recursion function should have a logic on why it should call itself, what it should do before it call itself, what condition should it call itself, and then it should have a base case. Yeah, it's called a base case. On the base case is basically to terminate the recursion. You don't want your function to keep calling itself. So a base case would be something to terminate the recursion. Maybe if something happens, stop, return the function. If something happens, stop. Yeah. So we're creating a recursion function. In the recursion function, we're going to pass a node. So a node is just a point on the tree. It could be this, it could be this, it could be this, it could be this, it could be this. But all we know is that the recursion will take a node. When the recursion take a node, the recursion will do two things. It will check. So first of all, we have a value outside somewhere, which is this 25, a value that we want to insert. What we do in the recursion is the recursion will do something. We don't care which node. We just want to take a node and want to do something on that node. Once we get to a node, we want to check if the value that we want to insert is greater than the node value. It's greater than the node value. If it is greater than the node value, we want to do one thing. We want to either go to the left or the right. Since it's greater, we want to go to the left. Sorry, we want to go to the right. So, for example, now if value was 70 or 100, we want to go to the right, right? So we want to go to the right. How do we go to the right? Well, we go to the right by going to the right. Actually, we go to the right by recursing again. You recurse, but this time we are going to recurse the node dot right. This is how we go to the right. Mind you, we are recursing because of what we do to this node. We want to do it to this node. So basically, if we go to the right, we want to ask ourselves the same question. Is our value now greater than the new node that we are recursing inside? The new node that is calling this function. Is it now greater than the node value? If it's greater again, we want to recurse again. But if it is not greater, else, that means it's less than, right? Else, that means else v is less than node. This is pseudocode, by the way. This is, I know it looks like Python somehow, but it's very far from Python. This is not Python, this is just pseudocode. So else we want to do recurse, but we want to go to the node dots left. Yeah, but now we just keep going to the right and the left or the right and the left. Our main purpose is actually to insert. So when do we insert? Yeah, looking at it, we insert at the point where you get to the leaf of the node, where you get to a point where there's nothing to recurse, where there's no node to recurse. That's when we want to insert. Yeah, that's when we want to insert. So that should be our base case, right? So let's say we recurse, we go here, then we recurse, we go here, then we recurse, we're supposed to go here. Now when we recurse and we pass node.right, we're passing an empty value to it. So instead of passing an empty value to it, that is the point we actually want to insert. That's the point we actually want to insert our value, right? We want to insert our value. So I guess we can use it as base case. So we want to say if node is empty, is empty, or is none. Let's stick to Python. Is none. We want to create a new node there that will contain our value, right? But then at this point, we're just creating it. We need to attach it. We need it to be part of this tree. So I guess from this point, we can return it. Now if we return it, that particular node that called it, so let's say it was this node that called it, that called this with function, we'll receive this new tree, so we can call it n. I'm running out of space, so let's just move it here. We can call it n. It will receive this, and when it receives it, we now want to attach it to the node. So we'll be doing the node dot, since it moved to the right before creating the node, we'll be doing node dot right equals to n. And same thing happens if it actually went to the left. If it went to the left, we'll be doing node dot left equals to, we'll return, first of all, we get our value that was returned, then we attach it to the left, yeah, and that should work. There's just one more thing. There's just one more thing. It's a recursion function, so everything will eventually go back to what eventually called it at first, which is this. So let's say I recurse and eventually I attach 100 here. I attach 100 there. 100 returns to 70. 70 then attaches the new node. Then at the end of the day, 60 that called it, right, would want to attach itself to n, to what this would return. If I don't put anything here, it will eventually return none. So 60 that called it would be expecting something returned, and it will store it here, and then we would now be attaching none to 60 again, which would eventually call it again and attach. Basically we end up with something crazy. This explanation is not very good. Let's go to the coding, you understand. Okay, so coding it, let's just do our recurse. So we are recursing, right? We're passing our node, right? We know that we eventually call this recurse function, so let's just call it now. We pass it root, and the question say at the end of the day we should return the root. So where's the question here? Return the roots of the node. Yeah, so inside the recurse function, that's what we want to do our logic. So the first thing we want to do if our value is less than node.value. If it's less than node.value, we want to recurse and we want to go to the left. Else it means that the value is greater than, so we want to recurse and we want to go to the right inside. RIGHT, yeah, right instead. Yeah, that's what we want to do. Now if we do this and we end up with our node being none, that means we've gotten to the leaf, and at that point we actually want to create the new node and pass our value inside, and now we want to return it. Now when we return it, we should be expecting it here. Let's call it new node. And let's call it new node. Now this is what I'm trying to say. We want to now attach our node dot left, in this case, to the new node, and in this case we want to attach our node dot right to the new node. But there's something missing, right? And what is missing is that, for example, let's say we're bubbling, let's say we've created this new node and we've attached it. The recurse function will eventually get here, which is not returning anything, and since it's not returning anything, it means that it's returning none. It will eventually get here and return none, and what called it will eventually pass none here, and then it will attach none to the new node. It gets crazy basically because of we eventually return, and not all the time we'll be returning from here. Sometimes the code will eventually get here and return null. So what we want to do is that we will actually want to tell it to return null if it gets there, and then we want to do some check. Our check will be doing that if new node is actually not equals to none, that's when we want to attach. If it's equals to null, we don't want to attach, we just want it to be. So same thing here. If new node is not equals to none, that's when we want to attach. So we want to be sure that our new node actually returned a new node before we attach. Yeah, and this should be good. So basically it goes like this. 5, right? Because calls from 4. 5 checks. Is 5 less than 4? No. It goes to the else. 5 is greater than 4. It goes here. This calls it to the right. Starts again. It first checks if 7 is none. 7 is not none, so it checks. Is 5 less than 7? Oh yeah, 5 is less than 7. Okay, I'm going here. I call it to the left. Now calling to the left doesn't exist. So instead of calling it, we just create a node and return. We eventually get it here. The new node containing this thing containing 5. Now we're going to check, is that node empty? If that node is empty, if that node is empty, we just want to keep going here and eventually return none. But if it's not empty, what we want to do is we want to create a new node. When we create a new node, we want to attach the new node that we created. So we're attaching it, and then we're returning none. So eventually this 7 will return none to 4, and 4 would not check, is the value not null? The value is none, so it's not going to attach. It's just going to go back up and keep bubbling up. Yeah, so yeah, that's basically it. Let's check if it works first. Yeah, we have to check if it works first. Yeah, it works. It works. And let's see if it submits. Okay, it doesn't submit. We have a base case. Sorry, if okay, let's just write the base case. So if root is actually none, we want to create a tree node, and we want to pass the value, and that is what we want to return. So if tree is, if we have a empty node at the beginning, we want to create a new node and pass in the value and return the value. Yeah. So let's see if this works now. Yeah, and it works. Accepted. Yeah, so I hope you understand. We are recursing, and as we are recursing, if we get to the lift node, we're creating the node, and then we're not checking if we actually created the node before we are attaching. If we did not create a node, we don't want to do any attachments. Only if we created a node. Yeah, and that is how we solve insert into a binary search tree. I hope you understand. Thank you.